All right, welcome everybody. This is episode 11 of Games with Go, where we're learning programming and and game dev. This episode is going to be about loading images from files and alpha blending. And before we start that, though, we're going to revisit our noise code from last episode, where we had parallelized our noise, and we're going to fix a mistake. So we had this this code right here, where we were trying to check to see if we had noise that was below the min or above the max once before we took a lock on it, which prevents any other Go routines from entering. And then we check it again and set it. And this prevents us from having to get a lock every single time through the loop, which made it fast. But Dave D on stream suggested we run the Go race detector on it, which can detect race conditions. And it found one. And I agreed that it had one, but I was wondering if this code would always work anyway. And I did some checking and on Reddit and found that found out why you can't count on it always to work. One reason is on some hardware, it's at least theoretically possible that hardware could make assignments like this not be atomic, which means the CPU might be halfway through setting max when we're checking it the first time, causing this check to fail, for instance. And the other reason is when the compiler compiles this code, it assumes that there won't be any data races. And with that assumption, it might choose to remove some of these if statements completely, as it might think, why are you doing it twice, for instance. So there's a couple ways it could go wrong. So we're going to fix it so that it can't. There's a couple different ways to fix it, but both of them involve keeping track of a min and max within each Go routine. So we're going to, instead of setting the global min or max, which resides outside the Go routine, we're going to make a new variable, and we'll call it inner min. We'll do one for max as well. We have to use colon equals because we're declaring and assigning a variable in one step. And then we can get rid of this entirely. And here we're just going to check inner min. And inner max. Get rid of these locks. Okay, so in the loop, we're just going to be working with a min and max relative for just our Go routine. Then once all of this is over, once the loop is over, we could then take a lock on our mutex. And then we could check if inner min is less than min, then min equals inner min. Else if inner max is greater than max, set max equal to inner max. And then unlock. Mutex.lock. So this way we're only locking on this mutex once per Go routine instead of however big the batch size is. This could be potentially millions of times per Go routine. So this would make the code correct and improve performance a lot. Another way we could do this is with Go channels. So, another change I made was I think previously we were just using 999 and negative 999 here. Go has a built-in constant for the maximum possible float, so you can use maximum possible float and negative maximum possible float so that your starting min and max values are safer. Okay, so another approach is to use Go channels. So channels are a special construct in Go. There's a built-in keyword chan for channels. And what a channel is you can think of it as a list that you can put items into or take them out from different threads at the same time safely. So a Go routine could put values into the channel. Another Go routine could take values out of the channel at the same time. Any number of Go routines, any combination, and it's not going to mess up. The adding values and removing values are atomic and thread safe. So we need to tell this how many things it could potentially hold right here. So we're going to put the mins and maxes in one channel. And so we're going to need up to number of Go routines times 2, because each Go routine is going to put one min and one max inside. Okay. And then we're going to do the same trick with inner min and inner max. But instead of doing the mutex.lock, we can say min-max chan. And this is a special syntax for putting things into channels. We're going to put in our inner min. We're going to put in our inner max. Then once we're all done, we can close our channel. Let's see, how does that work? Oh, we just say close. So this tells it that we're done with the channel. And once you've closed it, you can iterate over it with for say v. So this will go through each value in the min-max channel one by one. And then we can say if v is less than min equals v, else if v is greater than max equals v. Okay, that accomplishes the same thing using channels. We don't need the mutex anymore. And of those two possible fixes, the mutex one is probably more efficient. But I want to just sort of demonstrate how you can use, one way you can use channels. Okay? Any questions about that? Any questions about channels in Go? So Tangent asks, would it be better to do the final 4 in a Go routine? So one approach you could use actually, it wouldn't be useful to do this here, but if this workload were bigger or we had more routines going at once producing noise, it might make sense to make this a separate Go routine that can start going through the min-max values as they come in. So if you imagine you were generating noise for hours, spitting out their new mins and maxes, you could start pulling them out of the channel and computing the min and max at the same time that this is running. But since this is only going to be, eight values, this is going to take like a nanosecond, so it's not worth that complication. All right, we're going to go on to loading images from files. So let's make a new folder. Now I have picked some balloon images. So I'm going to call this project balloons, and I've got, I will give you guys a link to them. 1 second. So you should be able to hit this link right here. I guess I'll show it on stream as well so people can see it. I'm going to make a new file, balloons.go. So this is the URL, and you should be able to download a zip file that's going to have 3 PNG images inside. And you can drop those in your folder. So come on, Windows. There we go. So I'm going to take My balloons. And I chose balloons because they have alpha values in them that we're going to do alpha blending with. All right, so I'm dropping these image files into the directory. So now they're like, oh, VS Code shows them. I didn't even know that. Cool. And I also included credits here. These images are from opengameart.org, which is a really neat site. People kind of put art up that are sort of in the open domain on here. It's really good for using to like do prototypes and stuff. And then every bit of art has a license associated with it, which you need to read. Most of them require that you give credit. You should always give credit anyway, even if they don't require it. So thank you, Carrie Coombs, for your balloons. So these are images we're going to load. These images are PNGs that have alpha values associated with them. So like this area on the edges is completely see-through, and the balloon itself is partially see-through. All right, let's start with our basic STL code. That'll sort of be our framework. So just paste that in. And then one thing we need to do is we're going to use a package inside of Go that already has something called color. So I'm going to rename this to RGBA to avoid confusion. It's going to be a few other places. Yeah. Well, we're not going to do this anyway. So let's delete. This is the old code that drew the weird gradient. So let's delete that loop inside of our main function. And then we're going to want to have a game loop here that's constantly updating the screen. So take this chunk of code here. Let's cut that and put it down here inside of our game loop. All right. Cool. So we're going to want to make a function that can load one of these images from a file. Eventually, we're going to load all three and do alpha blending, but it's always good to take things one step at a time because we have never loaded an image before. So let's just figure out how to load one image to start. See how it works. So something handy about the Go language is as part of its runtime, it has a library for loading popular image formats. So we can actually load PNGs without having to use any third-party packages at all. And so you can import image/PNG, and that gives you access to functions that can load PNG files. So we'll add that import, and we'll also need to add OS if we don't have it already. The OS package provides some basic operating system functions like loading files from the file system. And that's what we have to do first. We have to get a file, and you do that with os.open, and you just give it a file name. And our program is going to be running from this directory, so we can just give it a file name like this, balloon blue PNG. And what this will return is a file object and an error in the usual Go way. And we need to check if error is not equal to nil. If error is not equal to nil, then we will freak out and print the error. Right? Panic will cause the program to stop immediately and print the error out. All right, now that we have our file, Oh, we can use defer to make sure we close the file when the function exits. Okay, so then we need to take our file and pass it to the PNG package. And PNG decode is what can decode that file into all the colors and pixels that are in it. So again, we get an image and an error this time. Check for the error. Just panic for now if we get one. Okay. Now we have an image. And you can kind of, if you're using VS Code, you can use IntelliSense to kind of explore the things available. Basically, what we have is something that tells us what the color model is for the thing we've decoded. Bounds, which give us things like the width and height. And at. In at, you can pass an X or a Y and get back the color at that pixel. So let's start and let's extract the width and height from here. So we'll say width is image. So bounds is a function. And we get the max.x. And height is equal to image bounds max.y. And then we're going to want to take this image object and actually get an array of bytes in the format that we're using to draw things with SDL. Because it doesn't come like that by default. So we're going to have to iterate over the image and make bytes out of it in red, green, blue, and alpha. So let's get an array of bytes ready. Array of bytes, and that'll be width times height times 4, because we have red, green, blue, and alpha for every pixel. And then let's keep an index into that array that's going to start at 0. And we'll say for y equals 0, y is less than height, y plus plus. For x equals 0, x is less than width, x plus plus. Okay, so the way that we get our colors out of the image, use the image.at function. And that returns a color. So and the color, so RGBA is a function. So this function, if you look at the IntelliSense, it returns multiple values. Just like we return like something in an error a lot, this actually returns a red, a green, a blue, and an alpha. And each one's a uint32, so we're going to need to change those to bytes. So we can do it like this: red, green, blue, alpha is equal to image.rgba, like that. Oh, we need to pass the x and y here. All right, so now we've got our colors, but they're represented as 32-bit unsigned integers. And even though they are represented as 32-bit integers, they are actually only 16-bit values. And the reason for that is because PNG have alpha, when Go decodes them, it does something which is actually really nice, which is it pre-multiplies the color values based on the alpha. So that means if you imagine something was red, but halfway see-through, so it had some alpha, the red would appear a little bit dimmer. It wouldn't be full bright red because half of it's see-through. So that sort of dimming of things is done ahead of time. So these values have some multiplication happening when they're decoded, and the 32-bit size gives them room to do that math without overflowing before they get to the final value. But it's a little bit non-intuitive. You think these are 32-bit values, so they should be divided by 2 billion or whatever it is, but you don't need to do that. So we'll start setting our balloon pixels. We'll start with B index, which started at 0. And we're going to have to cast these things to bytes. and divide by 256 to squeeze that 16-bit value down into a range of 0 to 255. And then we'll advance to the next index to set the blue, or G, sorry. And then we'll do that for blue and alpha, RGB, and then A. And then we need to advance one more time to the next pixel. Why is this still unhappy? Oh, this should be in file. Okay, so now we have balloon pixels. So if we want to see if it worked, let's just return those. So make this return a byte array. Then we'll go down to our main function. Oh wait, something is, oh, return balloon pixels. All right. So let's call load balloons. And balloon pixels equal to load balloons. And then we want to draw these pixels onto the screen just to see if anything worked at all. So we'll just draw it into the upper right-hand corner, which we should be able to do like this. So the screen buffer we have is pixels. And we're just going to set that equal to the balloon pixels. Well, actually, that's not going to work because it's going to, well, let's just see it. It'll look funny. Okay, looks promising. We got the right color, but you can see it's stretching it all across the screen because of the way we're copying these bytes here. So what we want is we're gonna want to build something like a texture. So up till now, all of our little games, like Pong, for instance, if we look at it, the draw functions are like literally drawing things every frame, right? So our paddles are actually drawing a rectangle every frame. The ball is like drawing a circle every frame, right? We're having to do the math to draw a circle over and over and over. But the way that games typically work, or game engines work, is you might do that work to draw a ball once, but you save it into a texture. And a texture is just a rectangular image, just an array in memory. And then each frame, what you do is you just copy that data. So like, for instance, these balloon pixels. You copy that into the screen buffer at a certain position, right? So you can move your texture around to animate it, or zoom in or zoom out by expanding it, but you're not having to redraw everything with math every time. And sometimes that process of copying the texture to the screen buffer is called blitting, or blit. So let's make a texture type. Let's make a texture struct, and it's just going to be an array of bytes. And we'll give it a width, height, and we might want to keep track of pitch. Pitch is basically width times the size of each pixel. This might be useful, so we'll keep that for now. And then we'll want a function that can take a texture and draw it to the screen. So let's see how we're going to do that. So we'll do we'll make a function that takes a texture pointer as a receiver, and we'll call it draw, and this should take a position, and the screen screen buffer to draw it to, which for us is our pixels. Cool. Then we're going to go our typical double for loop again. Oh, this needs to have a name. Call it text. Text.width. Okay. So these are going to represent the x and y values of the texture, but we need to translate that we also want to get screen coordinates for where we're going to draw this onto the screen, right, onto our screen buffer based on the position. So we're going to need to compute the screen y value. So we'll take the texture's y value plus the position y, right? So if the position of the texture is say 10, then we'll go 10 pixels down and then start drawing our texture from there. And then x will be same idea. And then we'll want to check to make sure that our the pixel we're about to draw can actually be drawn to the screen. So you can imagine a texture could move so where half of it is off the screen entirely, so we're not going to draw it. So we'll check that screen x is greater than or equal to 0, and screen x is less than the window width, and screen y is greater than or equal to 0, and screen y is less than the height. All right, so this guarantees that we're not going to try to draw outside of the array. We know we'll be drawing something that's actually in the window. So we'll want to convert our texture x and y's into a texture index. So we'll do y times text.pitch. This is why pitch is handy. You can skip the doing width times 4. Just do pitch directly. And again, the 4 is because we have R, G, B, and A. And then we need an index into our screen array. Do screen y times win width times 4 plus y or plus screen x times 4. Okay, so this will get us the index to read data from the texture and the index to copy the data onto the screen. And then we'll say pixels of screen index equals text or text.pixels of text index. And we'll do that for R, G, B, and A. All right. Undefined position. Okay, we'll make our position struct like we did for Pong. Okay, so now we have something that can draw textures. So we'll make a balloon texture. Actually, we'll have load balloons return the texture. So return a pointer to the texture. The texture needs our pixels, the width, the height, and the pitch, which is width times 4. All right, so now load balloon is going to return a texture. And we should be able to just say I have a habit of missing an O. Oh, need to give it the screen. and a position. Okay, so this will start drawing in the upper left-hand corner, if it works. There we go. We have loaded an image from a file and drawn it to the screen. So now that we can draw one image, let's load all of the balloons. All right, so let's make a quick array here. We'll call it, let's see. Let's do an array of strings. So we're going to do an array literal. So you give it the type, open brace. And we're just going to list all of our balloon file names. All the file names from over here. We'll put them in the array. And now we will iterate over all of these. So a big for loop. And we'll open each balloon string. Now we're going to end up with multiple textures. So our balloon textures. We're going to make a slice of textures. And it's going to be the size of the balloon stars. So doing it this way, making this the length of the balloon stars instead of just saying 3, guarantees that if you ever add more here, this will just work. You won't introduce a bug by adding more things to the string. That's a good habit to get into. And then balloon textures. Okay, so once each texture is done, we add it to our balloon texture slice. Then return our balloon textures. And change this return type to a slice of textures. Okay, so now we have textures down here. And we're going to need to draw all of them. And I'm going to move the drawing down here into the game loop. So we're going to start moving some things around a little bit. So for I comma text, let's do text.draw, and we'll make the position a little different for each one. We'll offset them a little bit. I have to cast that to a float because the positions are floats. POS, and then give it the screen. So let's see what we get. All right, we're drawing all 3 balloons, but as you can see, we have a problem. The alpha area of the balloons is not being taken into account at all. So we're drawing the red balloon and then the green balloon on top and obscuring it. We can't even see through the blank part of the image, let alone the balloon itself. So what we need to do is add something called alpha blending to our renderer. So our alpha blending will look at the alpha values and use those to mix it with the colors that are behind it. So you'll be able to see through the invisible parts and see partially through the partially visible parts. So let's leave this draw. Let's copy our, our current draw function. And we'll make another one called draw alpha. Because if we have an image that doesn't have any alpha, we won't want to use alpha blending because it's more expensive. Okay. So this is going to be tricky. So if you didn't know how to do alpha blending, like I didn't a couple days ago, because most people, when they do alpha blending today, are using OpenGL to do it, or letting SDL do it for them. They're not doing it by hand. So a lot of people probably don't know how it works behind the scenes. And there's different ways of doing it. And you can go over to Wikipedia, alpha compositing. We'll kind of talk more in detail about the math and different approaches to doing alpha blending. And if you go down here, you can actually see the formulas for it, which are not that complicated. And you notice here it says if pre-multiplied alpha is used, the above equations are simplified too. So this is the reason pre-multiplying alpha is nice. We talked about how the PNG decoder does that. So the R, G, and B values are already like pre-dimmed according to the alpha. So what this is saying is that our out value for our colors, R, G, and B, is equal to the initial value, or the source value, so like the image that we're going to draw onto some background, plus the destination color, so the current thing behind it, times 1 minus the source alpha. All right, and this math assumes you're using a floating point to represent your colors in alpha, floating point between 0 and 1. So ours is going to look a little different because we're using 0 to 255 rather than 0 to 1 floating point, right? We're using integers that are bytes. So it'll be a little bit different, but not too much. So we're going to try to keep this readable by pulling out everything into easy to read variables. So we're going to get our source red. So it'll be equal to, so we're going to have to make things integers because we're going to do some math which will make things bigger than will fit in a byte during part of the process. So we're going to get our source values for R, G, B, and A. Just keep incrementing through there. Then we're going to get our destination values. So that's the values that are currently on the screen that we're drawing onto. So destination R we're going to ignore destination alpha for now because the way we're drawing things, we're not going to need it. Okay, so now we can basically do the formula we saw on Wikipedia. So we're going to make a result R. So we're going to take our source R, and since we're not doing the floating point thing, we're going to kind of expand this so that we can do integer division on it in the end. So we're going to multiply this times 255 plus our destination R value times 255 minus source alpha. So that's sort of giving a percentage. So the destination R is a percentage of the source alpha. So the thing going in front of it, the more alpha it has, the larger the alpha value, the more of this will, or the lower this alpha value, the more of the destination value is going to end up showing in the result. Then we're going to divide that by 255 to scale it back down to between 0 and 255. And we'll do the same thing for green and blue. Green and blue. Okay, and then here we can actually ignore the alpha, the resulting alpha. So yeah, we just take our result R, cast it back to a byte. We have some mistakes. Source. Oh. So that, yeah, tangent caught it. So that mistake I made right there is actually, a lot of people recommend like never ever copy and pasting code. Like when I had just this, right? I copy and pasted it twice to do this quicker. The danger of doing that is you sometimes forget to change things. It's a really common source of errors. So I can't handle not doing it, but you might consider getting in the habit of never copy and pasting. But if you do, be very careful. RGB, 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 RGB. Okay. And that's a good reason, it's a good thing about Go not allowing unused variables to exist because it will catch lots of mistakes. Okay, so let's try changing this to drawing with alpha. Let's see what happens. Look at that. So we're definitely not occluding the completely transparent areas anymore. But are we able to see behind the balloons? It's kind of hard to tell. So let's move one of the balloons a little bit. Let's see something here. Yeah. Yeah. Okay. Um, let's take one of these balloons and just move it back and forth, which makes it easier to see if there's stuff behind it. So let's see, one way we can do that is we'll take the second balloon and we'll just move it a little bit. Back and forth. So we're going to make a direction variable equal to 1. And then this is balloon textures. Let's say 400 or why don't we have an X? Oh, well, let's give it an X. Or we'll give it a position. And then this won't need to take a position, because it's just going to have one. Someone on chat is asking if Go is the new Java. I would say no. Go and Java have similar syntax, but so do a lot of languages. So our textures need to have positions now. Hopefully Go can become as popular as Java, because I think it's better than Java in most ways. Hansi on chat asks if Go has a GC. Yes, Go has garbage collection, just like Java. It is optimized for lower latency, whereas Java is optimized for higher throughput. Those both have pros and cons. For games, usually lower latency is better than throughput. But games can be anything, so you never know. Games can be lots of different things. Okay, so let's see if this gets one of the balloons moving back and forth. Ooh, it does, but we have a... Oh, we're not clearing our drawing. Do we have a clear... Let's steal the clear function from Go, from Pong. We're going to go to Pong, take our clear function, add that up here, and we'll put that in our game loop. Oop, before we update. Oh, that's the wrong place to put it. Put it before we start drawing things. Hansi asks what I think of C#. I like C# a lot. It's what I use in my day job. C# also has a lot of nice game libraries for it. And of course the Unity 3D engine. I don't like that Go is JITted. I don't think that's a good thing for desktop apps or games. But it's not the worst thing in the world either. All right, so now we can see when our green balloon goes behind the red and blue balloon, we can see it. See how we have the partial transparency. So we now have functioning alpha blending, and we're starting to get the basis of a like basic kind of rendering engine here, right? We've got textures, so we can place the positions and render them in our game loop just by copying the textures to the proper place in the screen buffer. Right, so all we have to do to animate things is change their x and y values, and then redraw the screen, and they move around. Tangent asks if I wanted to have the green balloon move behind. Yeah, so right now, the order things are drawn in is just the order of the balloon texture array. So red will always be behind green, and green will always be behind blue, because it's going to draw red, then green, then blue. So when we're seeing this, the green is between the red and blue balloon. So you can imagine like the next kind of step you might want to do is have like like a depth for the balloons. So as well as having an X and a Y, you might want a Z, which decides which one is drawn first. And that's something we're going to get to soon. Next episode, we're going to look at how to scale these images, so like making them bigger or smaller. And you could use that to do like a pseudo 3D effect, as well as affecting the order in which they're drawn for alpha blending. And we're going to see how the challenges with scaling images, if you make them bigger, they're going to look bad because they're going to get blocky. And there's some techniques to smooth them out, but that is computationally expensive. So we're going to kind of see how that works out. Any questions from chat about what we've done so far here today? This is pretty cool stuff. Like most people who start game dev today don't ever do alpha blending by hand. Like I mentioned before, OpenGL can do it for you. SDL can do it for you too, which we're gonna see. We're gonna see that next episode. But now you'll know how it works, or one of the ways it can work, and that can help you understand how to use game engines. It can help you tweak their settings better. It can help you identify when things are wrong. Like if you see alpha blending not working the way you expect it to, knowing how things work under the hood helps you debug those problems a lot better. You can say, aha, it's probably this or that that's going wrong. All right, we got a few more minutes, so if anyone has any questions about anything or previous episodes, or have at it. I might do a little bit of cleanup here while we're waiting, so we'll see. Okay, yeah, one thing I do want to add is a frame rate counter. So I'll do that real quick before we go. So we've done the timing stuff a few times before. So this will look familiar if you've been watching. So we're going to get a frame start equal to time.now. And then down here, we're going to get a elapsed time. And we'll get that since frame start in seconds. We'll go ahead and multiply that times 1,000 to get milliseconds. And then as well, let's take the frame rate independent, or at least the frame rate limiting code we had from before in Pong. And let's bring that into here because that was good stuff. We've got this as milliseconds now, so this will be 5. And we'll do format.println. So we're going to print out the milliseconds per frame instead of frames per second, because that gives you an easier way to reason about changes. Like if you lose a millisecond, you lose a millisecond, whereas the difference between 200 frames per second and 201 frames per second is very different than 60 and 61 frames per second. It's harder to reason about when you do it that way. Oh, we've broken something. You don't need this times 1,000 anymore because it's already milliseconds. There we go. So we're going to use this performance counter to kind of see what happens when we start doing some of the extra functions we do tomorrow. We're going to see that performance gets to be a bit of a challenge with software rendering. All right, everybody, that's it for tonight. There's lots of stuff you can play with here. Like you could start do the homework thing. Things you can try, loading other kinds of images. Add this to Pong. You can try adding this to Pong and using use images for the paddles and ball instead of just the white circles we've got now. And just experiment with it. You can try some different techniques. Oh, here's something to try is see if you can speed up the alpha blending code. All right, so there's some potential opportunities to speed this up. Like One thing you should look for is something called loop invariance, which means if there's something inside of a loop that doesn't ever actually change inside that loop, you want to hoist it out. So the most obvious example of that here is screen Y is never going to change inside this for loop. So we can hoist that out, and that might improve performance. It might not, because compilers also look for that kind of thing. So the compiler may or may not do that automatically. In order to find out, you have to either measure the time this takes very carefully, or look at the final assembler that's produced by the compiler to see if it did it or not. But there's some other opportunities to do things like that in here that you could give it a try, measure it, and see if it makes any difference. All right. Good night, everybody, and thanks for hanging out.